Alright, hello, welcome everybody to the second video in a 7-part series, which is part of a larger series about music technology and things that I believe that every music technologist should learn and should at least have a fundamental grip and understanding about, especially if they want to be repairing their own equipment, building and designing their own equipment, and doing these more kind of like creating new hardware and tools. If they want to be that sort of creative technologies, these things are really great. All right, so today's topic is conductors, insulators, and semiconductors. So these are the 3 categories of materials that we have when we're discussing electricity and how electricity is able to interact with these materials in kind of a very broad, high-level sense. So from a high level, conductors are materials that allow an electric charge to pass through them easily. They have available electrons in their valence shells, which, if you remember from the last video, is the outside shell of an atom where electrons hang out that allows other electrons to enter into a valence shell and move onward. So they allow current to flow in this way. There's openings in the valence shells of these materials which allow for electrons to flow through them. Now, usually this is metals. So we're talking about copper, gold, lead, iron. But not every metal is conductive. And there are conductive materials that are not metals, as we'll discuss a little bit later on. But as a general rule, you can think of metal as kind of as a broad blanket overgeneralization. Most metals are going to be conductive. They're going to let electricity flow through them, right? And that's why we put rubber on, things that could possibly be electrified. And yes. The next material is insulators, which is rubber, which is something that we put on something that's conductive if we want to protect ourselves from being shocked. So an insulator is the exact opposite of a conductor. It prevents electrical charge from passing through. Technically, electricity can pass through any material if there's a high enough pressure or sort of voltage or energy potential between the 2 different sides of that material. But as a general rule, insulators are extremely difficult, make it extremely difficult for electricity to pass through them. So they, in contrast to conductive materials, insulators do not have any available electrons, and they do not then give or receive electrons. So they have valence shells that are stable meaning that they're full, that they don't have openings for these electrons to move through. And then they also have atoms that don't really have these extra electrons hanging out. So there's no extra electrons to really pass through, and there's they can't give away their electrons. They can't really receive electrons easily. Now, examples of insulating materials are rubber, plastic, glass, dry air. Even wet air is a pretty decent insulator. Ceramics is a really good insulator. That's what you see a lot in our power grid infrastructure to protect the power lines from accidentally hitting the wooden poles, which we'll discuss a little bit later. Now, the third type, which is something that we're going to gloss over in this discussion, because in-depth I'm going to do some videos that has a more in-depth chat about what semiconductors are, what they do, and all that sort of stuff. But for the purpose of this video, you can think of semiconductors as something that is in between conductors and insulators. So they, in general, have the potential to allow electricity to pass through them. But more important than them not quite being insulators or conductors in terms of how easy it is for electricity to pass through them, the most important thing about semiconductors is that they can change their conductivity. So they can change how easy or hard it is for electrons to pass through them depending on what we as humans do to them. And there's a variable range of resistance that semiconductor materials can possess, as opposed to conductors or insulators, which are very much on the poles and either have a very high ability to let electricity pass or very low ability to let electricity pass. Okay, so when we're talking about conductive materials, like I discussed before, a lot of metals are conductive. Silver is a conductive metal, so is gold, copper, and steel. Then you also have certain things that are not metals, such as water. Now, when I say water, an important distinction to make is that pure water, what you have in your Aquafina bottle, is not conductive. It's an insulator. It insulates. However, once you put a lot of impurities into water, it becomes more and more conductive. So salt water, and the saltier the water and the more impurities are in it, the more conductive it is. So the ocean water, seawater, is fairly conductive when compared to purified water that we drink. Now, even more so if you take water from the Dead Sea or take water from Utah's Great Salt Lake, that water is going to be even more conductive than seawater. All right. Insulators are going to be pretty much anything that isn't a conductor. Now, most materials will be insulators when we're talking about just materials in general around us. So rubber is an insulator, our tires, glass is an insulator, oil is an insulator. So just because dirty water is conductive doesn't mean that all liquids are conductive, right? Diamond is an insulator, rubies are an insulator, my hat's an insulator. Dry wood is an insulator. I kind of alluded to this earlier. So most wood isn't dry though. So the wood in a live tree is conductive, and plus trees do generate a certain amount of electrical energy in them to conduct their bodily functions, and in some cases actually communicate with other trees. However, if you get wood and then also wood that's been rained on, that's absorbed a certain amount of moisture, is going to be conductive because of the water going through it, which is sort of a little bit odd because pure water is non-conductive, but dry wood is non-conductive and wet wood is conductive. All right, so this is a great graph here that shows a handful of different insulators, semiconductors, and conductors, different types of materials, and it shows us how they compare to each other. On the top, it gives us a resistivity value, which is measured in ohms, and this is over a distance of 1 centimeter. Resistivity, more commonly would talk about resistance in electronics, is a measure of how difficult it is for electricity to pass through a device, or a material, sorry, and also a device or trace or whatever. So pass from one point to another. And so when we're talking about resistance, it has a value in ohms, and that the higher that value is, the more difficult it is for electricity to pass through that material. Now on the bottom, we have the exact opposite of resistance. We have conductivity. So the more conductive a material is, the easier it is for electricity to pass through it. So you can see on this wonderful image here that as our resistance goes down, as in we move from the left to the right along the x-axis, then our conductivity goes up. So the more resistive a device is, the less conductive it is. Excellent. So you can see, and this is like, so when we're measuring resistance, it is a linear scale. So 100 resistance is 100 times more resistive to electricity flow than a value of 1 ohm. So there's a direct relationship there, and you can see that we're looking at these, very, very large scales. So fused quartz on the bottom left has a 10 to the negative 18, meaning it's 18 zeros are or before that 1 in terms of its conductivity value, or on the top, or I will look on the top. So we'll look at this resistance. So its resistance is 10 with 18 zeros behind it. That's how many ohms of resistance it is. But then if we look at something like silver to the far top right, that has a resistance value of 0 with 6 zeros and then a 1. So huge variance. So of course we have the conductors on the far right. They're super conductive, right? They have a super low resistance. We have the insulators on the left. They have a super high resistance, and they have a really low conductivity, right? But what's important is, not now, but what's important to note is the semiconductor materials are in the middle. And you notice that things like silicon, germanium, cadmium sulfate, these have a range. Instead of just being a dot on this graph, there's a range of how resistive or conductive they can be. So in the case of silicon, which is the most commonly used semiconductor that we have harnessed, we go from anywhere from 10 to the 4 till about 10 to the negative 4. So we have a range of almost a billion x in terms of how resistive the silicon can be from one side to another. So that is important to note for later discussions, but for now we're going to focus mostly on conductors and insulators. The best way to think about this distinction, the best way to remember it, is by just thinking about a cable. So think about the cable that goes through your headphones, right? Or the cable for your guitar cable, or whatever cable it is. Now this cable that has electricity flowing through it is going to have a conductive material in the middle that conducts the flow of electricity. It lets it pass through, and then is surrounded by some sort of rubber or plastic, which then insulates this highway of communication, this highway of energy, from touching another conductive material and therefore causing bad things to happen, right? So it's ultimately anything that's conductive, electricity will pass through it. So we don't want to have the sound that is going through my guitar cable and the sound that's going through Jeff's bass cable to combine so that both of our amps are playing the same signal, right? So in order to make sure that we don't accidentally electronically combine the signals of our guitar and basses, we wrap this metal that's connecting our guitar and bass to the amplifier with a insulating material, with a plastic, so that if they touch each other, no problem. I mean, sort of, because there's a electrical field, a magnetic field that will interact between them, and we can get crosstalk and other issues. We'll talk about that later on. But we're going to do a quick little quiz here and try to figure out if we can determine if the following materials are conductive or insulative. All right, we got a brick wall. I'll give you a second to think. Is this conductive or resistive? So something like this is generally going to be an insulator. A brick wall doesn't really let electricity to flow through it because it's made of kind of soil, ground, earth, and rocks, that sort of stuff. As long as this brick wall isn't soaking wet, which appears pretty dry to me, it's going to be a pretty good insulator, so it's not going to conduct electricity very well. All right, what about this? So we have a body of water. Just to be clear, this is the picture of the ocean. It's not like a very big lake or anything like that. I'll give you a second to think. So if you remember, dirty water, as I like to call it, or water with impurities, whether it be salt or a lot of dirt, will be a decent conductor of electricity. So I pause to say it's like a great conductor of electricity, like a copper pipe would be, but it will conduct electricity millions of times better than water that is pure. All right. So I mean, I kind of gave this away, but we have fresh water here. Now, the distinction is I said fresh water, right? Like if I just gave this image, and even if it was just like a puddle on the side of the road, like that puddle would probably have a decent amount of impurities in it, whether it be a runoff from another location that ran down and then kind of settled there, meaning it picked up these minerals and pieces of dirt along the way, or even if like when the rain fell down through the atmosphere, it was really smoggy or something and picked up impurities through that. But as fresh water is a really good insulator, and it does not conduct electricity well. Now, fresh water is not easy to find in nature. I should say pure water, right, as opposed to fresh water, because like something like a lake or a river has a good amount of impurities to it, and it will be fairly conductive. But what you pour out of an Aquafina bottle will be a insulator. All right, wooden fence. Kind of hard to tell. It's hard to tell exactly how wet this wood is, quote unquote wet. Also mean like how fresh. Like if this wood was cut very recently and put up, it'll still have some inherent kind of moisture in it, and it'll be relatively conductive. But in general, wood is a decent insulator. Chainlink fence. Again, hard to tell 100% because you don't know exactly what metal this chain link fence is made out of, or if this metal has some sort of coating around it, like a corrosion resistance coating, which causes it to be non-conductive. But we can sort of assume that at least some parts of this fence will be conductive. We can make a broad blanket statement that the vast majority of metals are conductive. That's a conductor who is conductive. So we as humans are made of water a lot, and you can imagine this water is dirty water, right? So that's an oversimplification. Interesting thing about humans, and an interesting thing where you can do some fun stuff in terms of art or kind of manipulating these properties, the electrical properties of humans, is that human skin is very insulative. It doesn't let electricity pass very well. But inside of us, like the human flesh and bone is very conductive. Or not very, but it's fairly conductive. So that's the reason why tasers will shoot like two probes like into somebody's skin, and then it will shock them, because it needs to bypass the high resistance of people's skin in order to actually provide a shock. And in order to do that, it has to actually penetrate into the flesh. Acrylic. Acrylic's an insulator. It does not let electricity pass. And the same thing with glass. It's hard to tell what this is. It looks like just a rubber sheet. If this was just a rubber sheet, yeah, it's an insulator. It will not let electricity pass very well. But this is a special type of rubber called Velostat, and Velostat actually is a conductive rubber. And it's made with different densities to allow for its conductivity to change, and also for allow compressions to change the conductivity of it, or how resistive it is. And this is the sort of stuff that's used underneath a lot of like pads for buttons on computer music controllers, that sort of stuff, to measure how hard you're pressing down. You're sort of smashing this plastic down a little bit and changing the conductivity of it to measure. Car tires. Rubber. This is rubber. This is an insulator. This looks like a metal, so you could sort of assume as a blanket statement that it'll be conductive. But this is a gotcha. This is actually silicone. So this is what silicone looks like. Silicone's a semiconductor, but it looks visually like a metal. Same thing with this. This is germanium, which visually looks like a metal, but actually is a semiconductor. So you can be fooled by appearances and looks. And you need to know exactly what type of material it is to figure out if it exactly is a conductor or insulator. And then what about this? So we have a kind of a fun mixture of conductors and insulators here, and this will be the last sort of segment. So those interesting little discs that we see coming up to the wood, those are ceramic. Ceramic's a really good insulator, and ceramic prevents electricity from passing. The electrical cables, of course, are very good conductors, and they allow electricity to pass. And then the wooden poles that everything is housed up on top of, that's where things get interesting. So that's the reason why we have the ceramic discs there. Basically, wood is generally an insulator, generally if it's dry, it does not let electricity pass, but if it's wet, it can. So if we have a storm and if our power cable's up there touching that wood, then we could get some sort of electricity going down the poles, and it could potentially hurt somebody, right? So what we do, and you can see that we sort of have these routings of the electrical cable where the cable doesn't actually go through the wood or touch the pole. What it does is it goes up and over it. And we have those big, long, wide ceramic discs there to prevent that cable from accidentally flopping down, touching the pole, causing a circuit to become live and hurt somebody. All right, cool. So hopefully that was useful in terms of a broad overview of what conductors are, what insulators are, what conductive materials are, what they aren't, and then a little bit of a hint about what semiconductors are. And how they function in terms of their resistive values and their conductivity. So excellent. The next video is going to be on volts, current, resistance, and power, which are the 4 essential got to know values for describing electronic circuits, and is essential for understanding also how electricity functions. So we're actually going to use these to talk about analogies, to talk actually a little bit about the water analogy, and what it means if we have a high voltage circuit. How is that different from a high current circuit? How does that relate to resistance? And what is power if we're talking about electricity? All right, cool. Looking forward. Have a good one, everyone.